So thank you for Fumiya and also other organizers. It's a great pleasure to be here. Okay. So, oh yeah. Can you hear me now? Is that right?
Yes, we can hear you, Professor.
Okay. Okay. So today I'm gonna talk about sleep. And then I'm a bit nervous because you become very, very sleepy because of my how to say talk's contents. But let me do my best. And then I just came back from Japan a couple of days ago. I'm in a jet lag, and then I feel a little bit sleepy. Uh, s- uh, okay. So let me. So today I will touch upon some technological challenges to understand the molecular or cellular system within us. Okay. So, and also I like to touch upon a kind of a mechanism of sleep as well as the function of sleep. So function of sleep is quite mystery, but I like to touch upon that uh, function of sleep at the end of my talk. Okay. All right. So why sleep? So, medic. So, so sleep is important, at least in medicine, because it's related to the many, how to say, central nervous system related diseases, including schizophrenia and also depressions, as well as Parkinson's disease and Alzheimer's disease. So, every single like a brain-related disease has its unique, how to say, property of sleep. So unique symptom sleep. So I don't want to say sleep is a causation of these very important diseases, but I like to say sleep can be functioning as a very high sensitive sensor towards your brain status. So sleep is a kind of a fundamental status of your brain. So therefore, it's reflect of what's going on in your brains. So that is why I'm very much interested in sleep. But sleep is a little bit complex phenomena, biological phenomena. So therefore, it's a little bit difficult to work with. Okay. So therefore, we usually use such kind of a how to say complex system. We usually use the genetics. Okay. And then one of the famous example in biology by using genetics is initiated by the Konopka and Benza around 1971 when they identify the clock genes. Okay, so in your body or in your brain, there are clock. So approximately 24 hours clock. And then they use fruit fly to identify some mutant in which particular clock genes are kind of impaired. So therefore, for fruit fly, sometimes does not have a clock. Sometimes their clock is very fast, and sometimes their clock very slow. And then they identify the couple of very important clock genes. And then this work eventually leading to the Nobel Prize around 2000, I think 17, for the identification and cloning of the clock genes by Jeff Hall and also Michael Rauschenbusch, as well as Mike Young. But the sleep-wake cycle is a bit complex in human, at least in mammals. And then because we have, how to say, consciousness, we believe, and also our brain is a bit complex than fruit fly. So therefore, we have a kind of a double challenges. Okay, so compared with fruit fly, we are a little bit complex, meaning we have a lot of hypotheses, more hypotheses to test. Yet, we have a relatively weak tool to identify the molecular or cellular system. In other words, our genetics, I mean, mammalian genetics or human genetics is relatively slow. Okay, so therefore, we have more to test, but we have less tools to have. Okay, so therefore, we have a double challenges. Okay, so let me explain why our genetics is slow. Okay, so if you come up with some brilliant idea today, and then to test this hypothesis, it usually takes 1 to 2 years. We start with the single mice, and then we try to mutate the mice like a germline cells, and then we try to cross mate or cross or breed the mice a couple of times, and then finally we can get knockout mice in which particular genes are impaired. Usually this process takes 1 to 2 years because we are totally relying on the mating or breeding of the mice. And then one mice generation is usually 3 months. So 1 month to be born and then 2 months to be raised. So therefore, it's usually one generation is 3 months. And then we have to repeat this generation a couple of times, usually 5 to 6 generation, end up with the 1 to 2 years. And then if you are brilliant, and then if your idea is brilliant, and then if you are lucky, you can get let's say like a market phenotype. And then if you are a student, you will how to say get the PhD degree. And if you are a postdoc, if you become a PI, principal investigator. But if you are not lucky, you will get the very beautiful negative result. So, so therefore, it's a science. So therefore, sometimes it happens. But to avoid such kind of a, how to say, a little bit sad, say, situations, we try to shorten this process by using new technique called Triple-CRISPR technique or ES mice technique, in which we can generate knockout mice or knock-in mice without, how to say, mating or breeding. In other words, we can generate the mutant mice within 3 months or perhaps 4 months. Okay. And after we generate a bunch of different mutant mice, next step is to recording, okay? Record a sleep-wake cycle. But usually in mice sleep research, we usually perform the brain surgery, put the electrode onto the brain skull, and then try to record the electric activity of the brain. It took the how to say couple of weeks, and also it requires high skills, and sometimes it's not how to say easy, and also very tedious. So therefore, to avoid this kind of a situation, we also developed a new technique to measure sleep-wake cycle by just measuring the atmospheric pressure induced by the mice respirations. So we put the mice into the chamber, and then we try to record the mice respiration by measuring the atmospheric pressure change induced by the mice respirations. And then we succeeded to monitor sleep-wake cycle non-invasive manners. with very sensitive, high sensitivity and high specificity. And then we made a chamber by ourselves, and then we designed LAC by ourselves. And we are lucky enough to have some investment from the Japanese government to build the world's largest sleep, sleep measurements, kind of a facility in Japan. So every week we can measure more than 1,000 mice per week. Okay? And then by combining these two techniques, we can make a lot of knockout. For example, within our brain, there are famous neurotransmitter called acetylcholine. And then there are more than 15 genes associated with the acetylcholine, which is called acetylcholine receptor. And then we knocked out every single one of them. And then we found acetylcholine receptor, muscarinic receptor 1 and 3 has a pivotal role for the REM sleep. So when we knocked out two genes together in the mice, we found REM sleep, which is a little bit, paradoxical sleep called REM sleep. And then we usually have a dreaming during this sleep. But in this knockout, we get rid of the REM sleep or at all. And then we found in this mice, we found there is no REM sleep. Okay. That was a shocking result, and then which is covered by many newspaper, including UK newspaper. And it says, Japanese researcher, disruptive dream. Okay, so that was a little bit, kind of a harsh comment, but that was the first time for me to be exposed to the UK's critical attitudes. Okay. Anyway, so today I want to touch upon two things. So first, I'm going to talk about the mechanism of sleep, and then after that, I will talk about the function of sleep. So in sleep research, we are usually working on the many different topics, but one of the most important question in our field is called sleep homeostasis. So during the wake, we believe to accumulate sleepiness over the time, and then after wake, we become very sleepy, and then we have a sleep. Okay. For example, if you cannot sleep at all last night, you feel very sleepy now. Okay. So what is interesting here is time scale differences. So neural activity is usually millisecond to second, but a sleepiness usually lasts hours, even days. And then, so somehow neural activity of your brain, of your neuron, are integrated and then converted to sleepiness. Okay, so also we believe. But nobody knows what's going on in your brain or in your neurons. And then what is the integrator? And then what is the representation of this sleepiness? So that is one of the biggest questions in our field, I mean sleep research field. Okay. So there are famous hypotheses called sleep substances hypothesis, proposed initially by Dr. or Professor Ishimori, 1909, or Professor Pierron, 1913. So they independently found sleep substances candidate seems to be existing in the brain, and then which may make our brain sleepy. Okay? So they deprive the sleep of the dog, and then they extracted a brain and then injected the brain extract to the other dog, and then administrated dog becomes sleepy. So that is why they concluded there must be sleep substances. Okay. So after that, many researchers in our field try to identify the sleep substances, and then they propose a candidate for the sleep substances. But after that, many researchers tried to knock out the related genes, for example, receptor of sleep substances candidate, or enzyme, which may produce sleep substances, or ligand itself. But almost nothing happens. So we can observe very subtle effect in knockout mice, but it does not account for the, how to say, sleepiness much. So therefore, in our field, we are a little bit stuck for many years. So around 2012, I and my teams start thinking about a little bit different way. So we start thinking, what if there is no sleep substances? So to prove there is no sleep substances is very, very difficult. It's a kind of a devil's proof. So therefore, we start thinking alternative hypothesis. We start thinking, what if there is only wake substances? What if wake substances is enough? Okay. So let's suppose there is a wake substances. And then these wake substances are memorized some way. Maybe we can explain sleepiness. So we start thinking in that way. And then we start searching for the very important wake substances. And then we thought maybe calcium ion would be one of them. Because when you excite, almost always calcium go into your brain cells called neurons. And then without calcium, your brain cannot communicate. So therefore, calcium ion is inevitable. And also I have another personal reason. I'm a professor in Tokyo University Medical School Pharmacology. And then Setsuro Ebashi, who was a previous professor. And then he discovered calcium acting as a signaling molecules. So I have a little bit conflict interest. So in Japan, we have a little bit hierarchical system, academia system, and then we usually respect the adult person. And then, so that is why I start thinking about calcium ion as a candidate. Okay. So we thought maybe calcium might act as a source of sleepiness. And then, so that is why I start thinking about calcium, the role of calcium. But there was a kind of a challenging situation. So because directly relating genes calcium directly relating genes are more than 25 genes. So to test this, we have to make a knockout mice, every single of them. So that is why we try to develop a new method to make a knockout mice. Okay, and actually we made every single 25 genes knockout. And then we found calcium channel knockout And also we knocked out calcium-dependent potassium channel, and also we made a knockout for the calcium pump, and we found calcium, which is usually positive ion, so therefore, which make your brain excite. But what we found is a little bit interesting because calcium seems to be making you sleepy. So if you knocked out calcium channel, my sleep is shortened. And then if you knocked out calcium pump, in other words, calcium cannot go out from the cells. In that case, calcium ion seems to be higher. And then in that case, we found sleep become longer, meaning calcium seems to be acting as source of the sleepiness. Okay. And then after that, we thought maybe calcium is quite fast. They go back and forth between outside and inside cells. And then their dynamics is quite fast compared to the sleepiness dynamics. So therefore, we focusing on the downstream pathway. And then we found a couple of the calcium-dependent enzyme called kinase 2, which is a calcium-dependent enzyme to put the phosphorylation modification onto the proteins. And then we found a couple of kinase 2 family member called kinase 2 alpha and beta act as a sleep-promoting kinase. So based on that, based on these results, we proposed wake-related substances such as calcium act as a source, act as a sleep-promoting agent, and then eventually calcium make us sleepy, probably through the calcium-dependent enzyme. Okay. But you may wonder, is that true? Okay. So because calcium is a positive ion, usually once get into the cells, which make you excite. But yet our genetical data suggested calcium act as a sleep promoting factors. So the question is, which is correct? So if calcium act as a wake promoting substances, if you shut off the calcium entry, your brain becomes silent. Okay, but if calcium act as a brake of your neural excitation or suppressing your neural excitation, if you block the entry of the calcium, your brain become hyper excitations. Okay, excited, right? So therefore, to test this hypothesis, we also developed a new technique called cubic, C-U-B-I-C, which is a kind of a tissue clearing technique, which allow us to look at the, every single brain cells. So we started this technological development around 2010 or 11, and then we succeeded to find out some chemical which make your brain or mice brain transparent. And then, so we found this reagent also make primate brain transparent. And accidentally, we found this reagent make entire mice body transparent. And interestingly, by using this technique, we can look at every single cells existing in the mice brain, which turn out to be 100 million cells. And also, we found, we recently succeeded by using this technique, we can look at every single cell existing in the newborn mice. Okay. And interestingly, this technique not only applicable to mice, but also applicable to primate and even to humans. So if you are interested in this technique, please let me know. Oh, and also if you're interested in becoming first ever transparent human, invisible man or woman, please let me know. So I cannot guarantee you are still alive after this process because we, how to say, remove the lipid in this process. But I guarantee you will become, how to say, part of the history. So if you're interested in, please let me know. Okay. And then by using this technique, so we clear the brain of the mice after we administrated calcium channel inhibitors. So without the inhibitor, nothing happens. But with the inhibitor, I mean by shutting off the entry of the calcium ion into the brain cells, we found hyperexcitation of the brain activity, which is visualized by the uh, 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 particular protein called ARC, which is expressed in the brain cells after prolonged excitation of neurons. So, which suggests, or calcium might act as a sleep promoting factors. So after we published this paper, again, our study was featured by many, how to say, newspaper, including Indian newspaper, which says nighttime milk is good for your sleep. Okay. So I don't talk about nighttime milk, but there is some old wisdom which make you sleepy. So there are maybe some truths in old wisdom, such as nighttime milk. Okay. Anyway, so okay, so calcium seems to be important, but how about the calcium-dependent enzyme, such as CAM kinase 2? So if you activate CAM kinase 2, you can increase the 700 minutes per day sleep of mice up to 1,000 minutes per day. And then if you inhibit CAM kinase 2, you can shorten the sleep duration down to 500 minutes per day. Not only quantity, but also quality of sleep is also reduced down to 60% of the original quality if you inhibit this enzyme. And also, if you activate enzyme, you can increase the sleep quality couple of 10%. So meaning we can double the quality as well as the quantity. Okay. And then, so how they counted up sleepiness, we still don't know. This is a calcium-dependent enzyme. So therefore, all calciums go in, and then this enzyme will be activated. Somehow they are counted up by providing the modification of phosphorylation onto some proteins. And then within this enzyme, we found they, how to say, provide modification usually onto the other enzyme, but also this enzyme itself can be modified by themselves. And so therefore we investigated the details, and we found that first modification, how to say, induce sleep. And then we found second modification, maintain sleep. And then after we also found out third modification, and we found these modifications cancel the sleep induction effect and the sleep maintenance effect. So in other words, probably there is a opposing enzyme. Okay, so in other words, there is a wake-promoting enzyme, kinase. Okay. So therefore, we try to find out such kind of an enzyme, I mean, wake promoting enzyme, counteracting with the CAM kinase 2. And then we try to find the sleep suppressing kinase. And then if there is a sleep suppressing kinase, we might expect the sleep promoting reverse enzyme called phosphatase. So to search for these enzymes, we try to test at least 40 genes one by one. In other words, we try to make a knockout mice one by one. And then we found sleep suppressing kinase and also sleep promoting reverse enzyme called phosphatase. Okay, which is led by two grad students, Eman and Siu, and also Koji, who is a group leader in our lab. And then we found like a sleep suppressing enzyme called PKA, and also two sleep promoting phosphatase, calcineurin, and PP1. So details, name of each enzyme doesn't matter, but we found calcium can be a kind of a source of sleepiness, and then downstream of the calcium, there are calcium-dependent enzyme like a CAM kinase 2 or CAM calcineurin and PP1. Okay. And then we recently published this paper in Nature last year. So if you're interested in, please look at our original paper. Okay. So I skipped the detail. But in our paper, we also developed a new technique. So previously, we can only test the genes which don't have a lethality. So we can only work on the non-lethal genes. So in other words, so lethal genes means if you knocked out, sometimes mice will die. But regarding non-lethal genes, they are survive. So therefore, we can measure the sleep and wake. But some genes are very important in other process. So therefore, we cannot make a knockout mice. So in that case, we try to skip the developmental process. So after mice become adult, after that, we try to get rid of the particular genes, especially for the lethal genes. And then we developed a new technique to make a knockout mice after development to avoid the lethality. And then we tested. So in last year's paper, we also developed this technique. Okay. Anyway, and then so calcium-dependent enzyme are evolutionarily conserved even from the east. So in other words, this machinery at least conserved from the very beginning. So we still don't know single cell animal or single cell animal like a chlamydomonas or other let's say single cell animal have a sleep or not. But at least these enzymes are well conserved from the single cells organism. Okay. And also, we recently found anesthesia. So in the surgery, you usually, doctor usually use anesthesia drug, and then some anesthesia drug touch upon the calcium signaling. We still don't know the detail yet, but calcium seems to be making you sleepy. Okay. All right. So, all right. So currently, we found calcium act as a source of the sleepiness, and the calcium-dependent enzyme seems to be mediating and probably integrating the calcium dynamics to counteract sleepiness. And then the remaining question is, what is the executor of sleep? Okay. And then probably we skip the detail, but I just touch upon the essence of this topic. Okay. So during the sleep, your brain becomes slow, and then but are also synchronized with each other. Okay, which is called slow wave oscillation. In other words, we also use the term the words as delta puff. Okay, so or ketamine or some psychedelics or some sedation drug can induce higher delta power or higher slow wave oscillations. Okay, and also interestingly, these drugs can be used also as a rapid acting antidepressant. So you can use these drugs partially for the treating the depressions, right? And then, but nobody knows slow wave oscillation molecular or cellular mechanism yet. So therefore, we try to identify the molecular component, which may, how to say, explain about slow wave oscillation. And then we try to knock out at least 43 genes in voltage-gated potassium channels, and also some relating channels. And then we found the kind of a mechanism of slow wave oscillations. So here is the essence. So we found some slowly activating potassium channel seems to be very important to have a slow wave oscillations. And also HN channel seems to be important for the slow wave oscillations. So I skipped the details, but we recently found this, okay? So I skipped the detail here, okay. Yep, okay, so basically calcium is a kind of a tracking that your brain activity, and then over the time, calcium dynamics seems to be counted up by the calcium-dependent kinase, and also reverse enzyme called phosphatase. And then we still don't know the kind of a integrator yet. So which might be a kind of a channels we identified for the slow wave oscillations. We still don't know yet detailed mechanism, but these pathway seems to be identified by us and also others very recent years. Okay, and then the remaining question is, what is the kind of a function of sleep? Okay. So usually sleep is regarded as an inactive status. And then, so that is why in our field that are, very popular, and also like a kind of dominating hypothesis called synaptic homeostasis hypothesis, which basically says, during the wake, we learn, and then during the sleep, we forget. Okay. So during the wake, synaptic connection will be enhanced, and then during the sleep, synaptic connection will be decreased. So according to this hypothesis, which is understandable, and then which is very intuitive, easy to understand. But recently, we found sleep is not the inactive status, but in some sense, it seems to be very, very active status. Okay. So recently, we tried to monitor the sleep-like activity or wake-like activity in vitro by using neuron culture. Okay. So here, we can induce wake-like activity. So x-axis is the time, and then y-axis are different neurons, and then this color means a spike of the neurons. Okay, so during the wake-like status, neuron desynchronize with each other, and then we also can induce the sleep-like firing patterns. So in this case, neuron uh, um, show the slow wave oscillation-like firing patterns. So you can see the bursting here, and then you can also see the resting silent period here, and then bursting again, and then you can see the silent period again. So you can see the bursting, resting, bursting, resting, bursting, resting, like sleep, like firing patterns. And then interestingly, you can switch wake-like patterns and then sleep-like patterns by just manipulating calcium concentration outside the cells. So low calcium give rise the wake-like firing patterns, and then higher calcium give rise the sleep-like firing patterns. Okay. So when you look at the average firing frequency, wake-like patterns is always high. So here is a plot. But if you increase the calcium to induce sleep-like firing patterns, and we found that frequency become lower, average frequency become lower. Okay, and then interestingly, so average frequencies become lower, but when you look at the very closely and then look at the bursting frequency, in other words, if you look at the maximum frequency, we found maximum frequency become higher and higher in the sleep-like firing patterns. Okay, so which is quite interesting because brain seems to be, in a sense, brain become active at least for a very short period of time during sleep. Okay? So that is why we start thinking thinking about the role of the sleep in terms of the learning and memory. Okay. So therefore, we start with the Hebbian rules or spike time dependent potentiation, which is also another famous learning rules. So Hebbian rule is very famous learning rule. So fire together, wire together rule. So let me explain. So there are two neurons. If these two neurons fire together, in that case, neural connectivity will be enhanced. Okay, so spike timing dependent potentiation means there is a neuron A activate neuron B. Okay, so if neuron A activate and then neuron B activated, have a fire, in that case, connection between two neuron A and B, will be enhanced. Okay. In both cases, we try to test which is the optimal firing pattern to enhance connectivity, either sleep-like firing patterns or wake-like firing patterns. So according to Shy hypothesis, wake-like firing pattern will be optimal. Okay, and then sleep may decrease the connectivity. But what we found is quite opposite. So sleep-like firing patterns is optimal to induce connectivity, and then wake-like firing pattern is very, how to say, is not the optimal to induce the connectivity. Okay. So, and then we found sleep-like firing pattern seems to be kind of a optimal to induce connectivity. Okay, so that's interesting. So because average frequency is a bit higher in wake-like firing patterns and lower in sleep-like firing patterns. But when we look at the learning rule carefully, it makes sense because average frequency doesn't matter because or fire together, according to the fire together, wire together rules, if two neurons doesn't fire, nothing happens, meaning average doesn't matter. What is matter is maximum frequency. And then sleep-like firing patterns provide the higher maximum frequency. And also they are synchronized with each other, meaning according to the Hebbian law and the STDP, sleep-like firing patterns seems to be optimal firing patterns to induce connectivity. Okay. So therefore, we found during the wake, connectivity will be inhibited. During the sleep, connectivity will be enhanced. We named wake inhibition sleep enhancement mechanism called WISE mechanism. So we still don't know or to name new mechanism as WISE is wise enough, but it's easy to remember. So according to Shy, during the wake, sleep, connectivity is enhanced. During the sleep, connectivity is decreased. But according to WISE, other way around happens. So during the wake, your connectivity of the brain will be fragmented. And then during the sleep, your connectivity will be restored. And then interestingly, so we have a couple of predictions. So if, according to WISE, LTD-related molecule will be inducing sleep because during the in that WISE mechanism, during the wake, LTD occur and then sleep occur. So therefore, LTD-related molecule will increase sleep. And then, interestingly, we found calcineurin is quite important to induce slow wave oscillation. And the LTP molecule seems to be suppressing slow wave oscillations. Okay. So during the wake, connectivity will be decreased. And then probably some molecules, such as calcineurin, might sense lower calcium concentration to induce slow wave oscillations, and then which might restore the connectivity of the brain. So if this is true, we predict not only postsynaptic mechanism, but also presynaptic mechanism might be able to induce slow wave oscillation if you inhibit presynaptic transmissions. And actually, when we inhibit presynaptic transmissions, we can increase sleep and we can also increase slow wave oscillations. Okay. So, so according to this, we hypothesize, so during the wake, maybe fragmentation of the connectivity will occur. And then if, for many days, wakefulness, elongated, like working hard for the months, in that case, depression might occur because of the decreased fragmented connection of brain. But if you sleep well for a couple of weeks, maybe you can restore the connectivity of the brain, and then which might have an antidepressant effect. And also, it's interesting to know that some rapid-acting antidepressant drug have a property to induce slow wave oscillation. Okay, so maybe I will stop here. Okay, let me see. So okay, so today I talked about calcium seems to be important, and the phosphorylation pathway seems to be important for the integration of the sleepiness. And then also, during the sleep, your brain connectivity will be restored. And then during the wake, maybe your connectivity will be a little bit fragmented. So that is why to be creative or to be productive, you have to have a sleep. That's my main message. Okay, so thank you for your attention.
Thank you very much, Hiroki. It's very exciting to see how complicated sleep can be. We have a few minutes to take a couple of questions. There's one question. Could the increased need for calcium explain why excessive coffee consumption affects bone health?
Oh, I see. So coffee is a little bit complicated. So it's believed to be acting to the adenosine pathway. So it's believed to be acting through either adenosine 1 receptor or adenosine 2A receptor. And then if it's act on the adenosine 1 receptor, it might be have some crosstalk with what I taught. But if it goes through the adenosine 2A receptor, it's goes through the striatum or nuclear accumbens, and then from that pathway, we still don't know how these two pathways are interacting with each other. So we still don't know the latter case. And so, in short, we still don't know how coffee interact with calcium pathway yet.
Okay. There's one more question about how would signal from melanopsin affect the calcium channel or the circuit?
Okay, so melanopsin is expressed. Okay, so you said melanopsin or melatonin? Melanopsin, maybe.
Melanopsin, yeah.
Okay, so melanopsin expressed in the ganglion cells in the retina, and then its effect on the suprachiasmatic nucleus. So in other words, it's a center. Its effect on the center of circadian clock, and then circadian clock eventually interact with sleep homeostasis system. But we still don't know the exact mechanism yet. So each neuron, or at least many neurons, have also circadian clock system. So therefore, it's eventually probably interact with each other. I mean, sleep homeostasis system and also circadian system eventually um, interact. So we believe it's eventually interact with each other, but we still don't know the exact details. So interestingly, recently, Jonathan Lipton in Harvard University find out some clock protein are expressed in the neuron and also localized in the synapses. Yeah, and then interestingly, such clock protein interact with CAM kinase 2, which is a calcium-dependent enzyme, which is also involved in the sleep. But we still don't know exact mechanism, how circadian clock system interact with sleep homeostasis yet. But it's interesting questions.
Is there any animal that doesn't sleep or with abnormal sleep patterns?
Animal sleep is quite interesting, and then there are many diversities. So some animals sleep less, and sometimes they don't sleep much during summer, and then they sleep more during winter. So therefore, there are many diversities. And then we still don't know how sleepless animal kind of compensate sleep function during the summer, for example. And then, for example, reindeer don't sleep much during summer. And then they are kind of crunching during the summer. And then interestingly, their frequency, crunching frequency seems to be very similar to the frequency of the slow wave oscillation. And then we still don't know exact mechanism, but there are some hope or hypothesis. Some brain activity might mimic the function of sleep, such as crunching, but we still don't know. Maybe some DARPA or military related study might be very much interesting in this compensation of sleep by using the other brain function, but we still don't know yet.
Question from me related to the previous question as well. Did your research find out whether there's a relationship between an animal's body size or something about the body rather than the brain activity to their sleep?
Oh, I see. So slow wave oscillation quite well conserved. Frequency is similar between human and mice. For example, slow wave oscillation is, or delta power defined as a frequency from 0.5 hertz to 4 hertz. So it's a quite very slow range. And then it does not kind of a change. It seems to be not changing due to the body size. But right. But it's related to the usage of the particular body part. For example, so there are some phenomena called local sleep. So if you use left-hand side, how to say, body part, and then your right-hand side, how to say, brain activity seems to be sleeping after exercise, not the left-hand side. And then these local slow wave activity might reflect the usage of the particular body part. So therefore, sleep seems to be not a global phenomena, but the local phenomena. And then these local phenomena, local sleep, usually communicate with each other to have a global sleep. But a very essence, very basic component seems to be embedded into the local circuit or local cells. So frequency doesn't matter, but maybe sleep maybe can be executed locally. So that's what we know.
Thank you very much. And it was great listening to you, Hiroki, today. And there's a couple of questions in the chat as well. If you are going to be around with us for a while, please have a look at the questions as well, so you can reply directly to the participants.
Okay.
And we will have short talks and panel discussions as the next session after the coffee break. And if you're going to be around, please join us for the discussions as well. So these discussions will follow up after the short talks, starting from 10:30 onwards. There will be 3 talks and a panel discussion afterwards. So you're welcome to join us if you are around.